So, good morning everyone. We are covered the halfway of the course and so many things to be covered, and Professor Misra was busy in preparing slides because he has to take next 4 day classes, right, and every day 150 lectures mean to 600 slides, right. It is a lot of thing to do. So, he will not attend today, but he is preparing for tomorrow's. Okay. So, today I am going to talk about this the security of compilers, okay, and the title of the talk is your compiler secure? The question I am going to ask, is your compiler secure? What is your thought? Is it secure, not secure? Yes, not secure, obviously, otherwise I will not bring this here, right. Okay. So I will talk about that in more detail, and whatever the kind of work we do to verify the security of compiler, that I will talk about, but purpose will be to just give you the concepts, not the exact theory behind that, right. So, we basically try to give you the core intuition behind this. So, I will talk about the compiler, the background of this security problem, and then 4 different kind of things that we have done so far in the last few years I will talk about. So, everybody aware of what is compiler, what compiler does, right. So, with general purpose processors, processor has a set of instructions, right, which it can only execute only a specific set of instruction, nothing else, but you are allowed to run any program on it, right. So, how it is happened is basically you have a compiler which is basically sitting in your operating system. Whenever you write a C program, say, it convert into the machine instructions, right, which that particular processor understand, right. So, now you can write C, C++, Java, any programming language program, so that there is a compiler which can convert your high level language things into the machine instructions, and every processor has a set of instructions, and it depends on the processor architecture which kind of instruction it supports, right. So, it has this steps is basically the lexical analysis, syntax analysis, then semantic analysis, then after that you generate the IR, intermediate code, and then this compiler code optimization happens, and then you generate the target code. This is basically the binary, right. So, it is basically if you have something, say, so suppose you have some add operation, right. So, add so effectively you are doing R1 in the original program, there may be a variable a equal to b plus c, right, and then this a maps to your register 1, then b maps to register 2, c maps to register 3. So, this is your actual operation is happening, and this is your assembly level program which is also still readable, something like this R1 equal to R2 plus R3. So, this will be converted into the machine instruction. So, add maybe say 1011, right, depends on the number of instruction it supports, right. If there are 5 bits, then in 32 operation it will support, and then R1 may be denoted by say 101, then R2 may be 111, and R3 may be 000. So, you will effectively get a bunch of Boolean values, right. So, it is basically that will be the outcome, and once this goes to the processor, it understands this is add, this is basically the value will be stored in R1, this is nothing but R2, this is R3, right. This is the final outcome starting from a program in high level, right, and this program has lot of other syntax like loops and all those things, right, loops, if else and all. So, I am not going into all detail what is happening here, but this is the kind of steps, right. It basically parse the check whether you have a syntax error or not, then it's whether it's following the grammar of the language and all. So, those things are checked. So, if you come here, that means there is no problem in your program, at least it will going to execute, right, and this is your IR which is in terms of the 3 address code that I have already talked about in the that HLS thing, right, and this is where lot of code optimization being applied by the compiler, right. And if you open any compiler book, you will see hundreds of such optimizations, okay. To give some name like say common sub expressed elimination, dead code elimination, then copy propagation, constant propagation, various loop optimizations. So, if you open any compiler book, you will say hundreds of such optimization being used, and why those compiler optimization being used by the compiler? Any idea why this optimization to be added?
Reduce processing time,
Yeah, exactly. So, it is basically, as the name suggests, is optimize your program, right. So, it try to reduce number of instruction to be executed, maybe unnecessary code to be removed, unnecessary duplicated computation can be removed, and so on, right. So, it basically optimize your code, so that your runtime of the code will be reduced, right. There can be many optimization parameter, maybe try to reduce your time, something maybe instructions and so on, but finally, this is being applied before being converted this assembly to this machine learning thing, machine instruction thing. Okay. So, this flow everybody is aware. So, our focus, so these are very standard thing, right. We are not making any modification to the program, right. Here we are just checking whether your syntax is correct, your semantic is correct, and all those things, right. So, we are not making any changes to the program, right. The main changes is happening here, right, because you are applying compiler optimizations, and that may change one program to another, right. So, this is a point of concern for us, right. So, since you are giving one, so you think about you have a AES code which is very secure, you make sure that there is no information leakage anything, but once you go through this code optimization phase, it might apply various optimization, right, and that may change the code structure. So, we are focusing on this code optimization part, and we will see whether this actually safe or not. Okay. And this is also straightforward, because once you done this, you have to just convert this into this, right, which is also kind of straightforward. So, our point of concern is code optimization phase of compiler, and we will look into in detail what are kind of things happening there and whether they are safe in terms of security. Okay. So, so this is what the role of compiler optimization, already your friend suggested that it enhances the performance of the code, improves the execution time, determines the less resource, right, demands less resource and efficient memory usage, and so on, right. So, this is a well researched area. Maybe people are now working on say machine learning compilers and all, what kind of optimization is good for machine learning applications, but this for traditional compiler like GCC, these are very well researched areas. Now, correctness of compiler optimization. So, first of all, when you optimize the code, we have to check whether the modified code or optimized code is functionally correct, right, in the sense whether that is equivalent to the original program. You have to ensure that, right, you are modifying internally, but you have to make sure that your original program and the modified program or optimized program is are equivalent, right, that has to be there. So, so that means the verification of this compiler optimization correctness is again another very big research area. So, there are a lot of work has been done in this domain, because there may be some cases that modified code may not be functionally equivalent, and whenever you implement any optimization, you have to ensure that this is basically functional equivalence, right. Checking functional equivalence means your original program and optimized program are functionally equivalent. Okay. So, this is well researched area, and this is not point of discussions today, because this is, if I have to start, this can be a complete course here. So, now the question that we are going to ask is, does the correctness equivalent to security? So, that means I have proved that your source program, so this is your source program and this is your optimized program, you convert into S into O, and you have shown that S is equivalent to O, right, or you can write this is equivalent to O, but does this means they are equally secure, right. So, this is the question, right. So, we are taking all these optimizations which are already proven to be functionally correct. That means, the source code and optimized code are functionally equivalent. In those scenarios only I am talking about, does this mean also secure. So, so we will basically see whether that is true or not. If not, then we need further analysis, right, to check security. So, I will give you an example, dead store elimination, which is something a very well known optimization, and every compiler does this, right. To give an example, say suppose you have a function where you basically you read the password and you check whether the password is correct. If it is not, you say it is incorrect password, give the next password. Otherwise, what you do, you just do x equal to 0, that means you clear the password from the memory and then you do rest of the things, right. This is very common, that you read the password, check it and clear it. But when you give this particular program to any compiler GCC LLVM, it will identify this particular operation is dead code or dead stored, right, because this value of x will never be used in the rest of the program. So, it will identify this instruction is basically dead, it does not, you do not need to execute this particular line. So, what it will do, it will write everything same, but it will remove this particular operation, just thinking that this x equal to 0 is useless to me, because it is just doing unnecessary operation, I will need basically one clock to execute this, I will not do this. So, these two programs are functionally equivalent, because your final outcome of the program will, of the source program and the transform program will be same, right. So, this is functionally equivalent, but does this two equally secure, that is the question, right. What is your answer? So, which is more secure, the left hand side, what is the intuition?
Sir, because here the password will be kept to 0 and it will be, I mean the original password doesn't get written here.
Yes, exactly. So, it is a very high level, how attacker will take advantage of this is basically is a much more things to be discussed, but very high level, this password is remain in your memory only for maybe a couple of clock cycles. Here this password will remain in your memory entire execution of the program, right. So, that means that it gives more opportunity to the attacker to get the password, because he can do many kind of attack like cache attack on any other things, he try to get rid the value of x from the register where it is stored, right. So, since you are keeping that value for more time, it is give more opportunity to the attacker. So, that is the kind of bottom line. So, it is basically this is not secure, right. So, ideally compilers should not remove this, because this was added purposefully by the programmer, so that he does not want to keep the value of x in the memory for longer time. Okay. So, this is what we basically conclude, that something may be correct, but not secure, right. And I can show you many, at least 10 examples of the similar kind of optimization done by the compiler, and every time I can show that the modified version is not secure. Okay. Then how do you measure the security, right? How do you measure a security of a program, whether it is secure or not secure? There should be some parameter, right? This is better than this and all, right? There are many ways you can do. It is basically I mean checking by fault injection or using the memory power, all those things I have already discussed. But usually in this discussion I will mostly talk about the information flow, right. What does it mean by information flow? It is basically flow of information from one variable to another variable, right. And here the kind of program I am talking about is the program which is the kind of program in which you have some sensitive input, right, or secure input. You think about an AES algorithm, what is the input of AES? You have a plain text and a key. So, plain text is not secure or untainted, in this terminology it is called untainted, which is basically kind of not secure, or tainted, which is kind of secure input, secure or sensitive. So, I will only talking about those program in which you have some sensitive inputs or tainted inputs, right. And our objective is, as Professor Mishra also was discussing in the previous class, that I have to see how that value of sensitive value is flowing through your program. What are the other variables also having some part of that information, right. So, in that case people will not try to get the sensitive information directly from this, but the other variable where that value is indirectly stored. Okay. So, this is what we are talking about, and we have to make sure that we have less such information flow from tainted to untainted variables, right, because if you move some tainted value to this, those variable also become tainted, right, because that variable also can now be point of attack for the attacker. You understand the point? So, in general we have two kind of information flow. I will talk about little bit details. So, I want to make it very high level, so that you can understand the basic concepts. Okay. So, there are two kind of information flow. You understand what is information flow, right? So, we can have explicit flow. Say for example, you have a variable age which is sensitive. I am just talking about high and low here, just to give you the feel, and the low variables are the not so important variables and not sensitive information, right. So, now if you do this x equal to h, so there is a direct information flow, right. So, now if you can attack x, you will also get h, right. So, this is what is called explicit flow. So, data is explicitly flowing from one sensitive variable to another not sensitive variable, and that is explicitly happening, right, which is much easier to detect. There is the other one is called implicit flow. What it does, let us say I have a sensitive variable h, and I am checking if h greater than 0, then I am doing x equal to 1, otherwise x equal to 0. So, does there any information flow from h to x here? Yes, no?
No sir, actually I mean the sensitive information is doesn't flow from a.
Yes, apparently there is no direct or explicit flow, right, but there is information flow. I will talk about why. Let us say I run this program for one time, and I can see that, see, because maybe my x is output, I can see the value of x is 1. I can clearly tell that h is greater than 0, your sensitive information is greater than 0. It is not the exact information of h, but I get some partial information about h here. So, this is called implicit flow, right. So, I may not get the all information about h, but I have early get some partial information, and I exclude all the possible value of h which is less than 0, right. So, that is also some information. Just reading the value of x, I can identify that h is positive value, right. So, that is the kind of the implicit flow, right. So, in program identifying explicit flow is pretty easy, right. The problem happens with the implicit flows, and we need kind of sophisticated mechanism to identify what are the this implicit flow in the program, and you think about whenever you have a loop and you have branches. So, then this problem will come, right, and I will talk about more how do you do that. Okay. So, I will try to my attack is basically based on this. I will try to figure it out what are the explicit and implicit in the program, and if you take the source program and the optimized program, are they same, right. That is the kind of point of our interest. Okay. So, this is I have already discussed that this this value is gone, right. So, this is okay. This is not the same example, the same example, but the another optimization called static single static assignment, right. Do you know what is SSA in a compiler domain? Single static assignment. From the name you can make out what is static assignments, single, no. So, effectively it says that in your program, if you have a variable getting assigned multiple time, I will make sure that one variable will assign only once, right. It will be defined only once in your entire life cycle of the program, right. That is why this is single assignment, okay, static assignment. So, here what is happening, so you are assigning x equal to password once and x equal to 0 once. So, same variable is assigning twice, right. So, if many compiler does this to do lot of optimization, I will show you an example also why how this will help in reducing the number of register needed in your circuit in after some time. But this is a very common optimization, and every compiler does this by default, right. You have to explicitly stop it. Okay. So, what it will do? It will basically create two variable for x, right. So, it will basically create x1 and x2, so that every variable become defined only once, right. It is there is a single assignment. So, did you understand this? This has all variable is assigned exactly one, x1 is assigned once, x2 is assigned once. Here x was assigned twice, right. So, this is single assignment. So, this is again creating the same problem, right, that this x1 now will store the value entire execution, but here it was overwriting by 0, right. So, this is what this the concept of this correct and insecure, but so we basically concluded that your functionally correctness does not ensure the security, and I have given two examples, right, that is coordination and single assignment form. So, now I will bring the concept of relative security, because we are talking about compiler optimizations. You have a source program and optimized program. What is your concern? Your concern is to make sure that your optimized program is as secure as the original one, right. You might have that your original program was less secure, but you make it more secure, which is very good for you, the compiler is helping you, but it should not be other way, right. That means, your target program or optimized program should be as secure as the original program, right. So, T should be or T must be so, this is what is my objective. If compiler create a version where your T is more secure, which is good for me, but I cannot make T less secure, which is happening in my other examples, right. So, for example, in this example this is more secure, this is less secure. So, which is not good for us. I do not want to allow that kind of optimizations, right. Now, if you take this example, you have SSA, but during register allocation, I will talk about register allocation in more detail. It may map that the lifetime of these two variable is non overlapping. So, they will map x1 x2 into R, right. So, single variable. So, which is good for us, right. So, earlier x1 was leaking the password, now R is not leaking the password. So, that means, here optimized program is more secure than S, which is good for us, and I do not need to check that thing. Okay. But what I have to check is this part, right. So, whenever you have this is more secure, but this is less secure, right. So, this is basically optimized code is more leaky than the source. This is a point of concern, and I should have a mechanism to detect this scenario 2. Understood? So, the objective of the compiler should make sure that your T is as secure or relatively secure to S, that means as secure as S. Okay. So, this will be our objective. Understood? So, we are going to check the scenario 2 where the optimized program is less secure than source program, and we have to detect that. Okay, understood? Any question? Okay. So, so this is not something we are only doing in the world. So, this is a serious problem, it has been identified maybe few years back, and people initially was trying to make this optimization secure, right. So, they try to modify this optimization and make a secure version of it. Okay. So, it is basically secure date store elimination, secure single static assignments, and so on, right. These are the kind of work you will see in the literature. Okay. But what is our point is that there are hundred of optimization, as I mentioned. Making all secure version is not so easy, right. You have to make lot of modifications, right. So, so one way of going forward may be that. So, this is basically secure compilation, right. So, the term secure compilation is you make sure that your compiler is secure, it does not introduce any security flaws, right. So, that is a good thing to do, but because this compiler has hundred of optimization, it may be difficult practically to implement a secure version of all of them, right. So, one practical approach will be that you cross check, right. You optimize with the normal one, and you cross check that whether your optimized program is as secure as or the original. If it is not, you basically do post fix, right. You make some small changes so that your program become as good as the original program, right. That can be a practical approach, right. And our way forward is that only. So, instead of making individual optimization secure, what we tried is that we try to develop a combined process where we identify the leak in a program, and then we try to think about how to post fix that. Okay. So, that is one direction of work, but I will start with the register allocation. So, this register allocation is another important step in the compiler. As I have shown the example, right, you have a plus a equal to b plus c. Finally, this a b c will not be there, because your hardware there will be some set of registers, and those a b c will be mapped to the registers, right. So, that mapping of variable to the register is register allocation, and I have already shown the similar concept in high level synthesis discussion, right, in day 2. So, this register allocation is also an important step in the compiler flow, and I will show that this is also is a point of concern, and it actually leaks information, okay, which we have been studied, and we have shown some way to fix it. Okay. So, I will just give you the conceptual idea. So, that was the idea, and that the relative. So, this is our first idea that we have I will present. Second idea is that how do you, given a program, how do you identify the overall leak of a program, right. So, this is using the tent analysis. I will talk about more detail of that, and then it has a problem. So, by default there is a tent analysis, which is a very well known technique, but we basically identify there is a over tenting and under tenting problem, and we come up with a method which actually have, I mean, which basically improves on tent analysis. So, just to give you the idea what is over tenting and under tenting, let us take this example, because I think it is better to take small example that will give you the core idea, right. Say you have this program, right. What is happening here? You have some two computation is happening here, and your sensitive value is basically h. Okay. So, I give the name h just to identify the sensitive high or low, right, and you have something like this. So, in this case which value become tented now? Tented is basically if that explicit or implicit flow that I talked about, right. So, in this program which value is become leaking now, which other variable? So, you have h is sensitive, and if you execute this program, which other variable will leak h, right. I have given that implicit example, right. Which is the other variable? A. Yes, you are right, because now from the value of a, because if you take this if flow, then it will be b minus c, and if it is go to else, it is b plus m. So, value of a will change, right. So, since I am controlling b, c and m, I can tell whether h greater than 0 or not, right. So, that means in this program a is also leaking, right. So, what are the leaky variable? We will talk about the leaky variable. So, a is the leaky variable, right. So, now there is a very well known optimization called code motion. What is code motion? As the name suggests, you can move your operations in the code, right, and there are many advantages. You try to reduce the lifetime of the variable, or you try to reduce the number of operations to be executed in the program. So, those are the advantage of code motion. So, in this context, say it decided that it try to move both this operation inside the if else block. Okay. So, now since a b is being used both places, so this operation has to be move into both the branches, right, because b is being used here, b is being used here. So, I am removing this b equal to x minus y here as well as here, makes sense. But what about c equal to x plus y, this operation? It is not being used in the else part, right. Yes. So, now I will move only this c equal to x plus y here, because here, right, because only c is being used here and this c is not being used here. Everybody understand this? Should I repeat? No, right. So, the code motion logically will do this. It will put b equal to x minus y in both places and c equal to x plus y only in this if branch, which will save one instruction if I go through the else part, right. So, this is the kind of benefit when you do compile optimization, right. So, if in 50% time if you say that value of h can be 50-50 positive or negative. So, if I go through the else branch, I will execute one less operation. Okay. So, now in this optimized program, what are the variable is leaking? H. Earlier it is a, right. So, here it is only a, this is the leaky variable, right. Here obviously A is already there, right. So, if you do this tent analysis, if you assume that whatever variable is there in the branch is leaking without thinking anything else, then you will say that B and C also leaking, right. Understood? Should I repeat? So, if you assume that anything inside the branch is actually leaking the information if that variable is sensitive, then all this B, C and A are all leaking because they are executing inside the variable in the program. So, if you go by this idea that everything inside the branch is actually leaking, it will say ABC is actually leaking, right. The leaky variable is ABC and earlier the leaky variable was A. So, it will say that there are more leakage, right. Now, if you look into very carefully, does B leaking H? No, right, because it does not matter whether you go to the if branch or else branch, your value of B will be same. So, what is our core idea? That the value of V should be different if I go through if branch or else branch, which is not happening here. So, actually B is not leaking, right. So, the leaky variable, but C is leaking, because if you go through H now, C will leak, and if you go through here, C value will be garbage, right. So, there will be a difference in value of C. So, the actual leak is this, right, A and C, okay. Understood? So, in general, if you do this over-tenting problem, then it will identify false positive, that is what I try to mean. So, false negative, that it identify this B, and but it is not, and if you ignore the implicit leak, that I will not consider implicit leak, then C will also be excluded, right, which is also false positive, right. So, that means either if you consider all of them, that is also a problem, if you ignore all of them, that is also a problem, right. So, that is what is the problem with tent analysis, and we come up with a more precise analysis to identify the exact leak, and that I will discuss in a moment. Understood? So, I will now give you another interesting problem issues, the problem with tent analysis of loop, right. So, if you have a loop in a program, what are the issues will come when you do with the tent analysis of loop. Okay. So, you will see here, let us say I have a loop like this, right, it is a for loop or while loop, what it is, right. So, you are doing if x less than I, you do B equal to A, then you do A equal to password and I equal to I plus 1 and come back, right, and until x less than A, you will go do this loop, right. And since your I is getting change here, it may be other way, right. So, it basically A, the value of I is getting increased, but not x, right. So, it may be not of x and this is x, right. But it is basically until your x less than a I, it will execute, and after that it will not, right. So, now you see about if you just execute the loop once, I what are the value is getting leaked. So, if you loop execute once, your password is a sensitive value, right, PW is the password. So, after the first iteration, which value is become leaky? A, right. So, A is leaky. Now, if you execute second time, your value of A become assigned to B also, then B will also become leaky, right. So, that means if you have a program like this, the loop if you just execute once, you may not get all the leaky variables. You need to execute multiple times, right, to identify what are the variables leaking inside the loop. And I give an example like this, right. Now, if you iterate third time, will there be any more variable to be leaked? No, right. So, that is called fixed point, that I start with 0, in first iteration I got A, second iteration I got I have added B, third iteration also A B, that means there is no further variable, I will stop here. So, identify the loop leaks in the loop, you need to execute the loop multiple times to identify the overall leak of the program, Okay. So, that was also not properly handled in trend analysis, but these are the things to be done to develop a practical algorithm, which will identify all possible leaks in your program. Understood? Okay. So, that is another contribution. So, these are the kind of primary thing we have done, that we basically prove that your register allocation is not secure, and we come up with a secure version, and then given a program we try to identify the precise loop leak corresponding to the branches, precise leak corresponding to the loops, and then we come up with a method which can identify the relative security between two programs. Okay. So, that is the kind of contribution we have. Okay. So, I will talk about this SRA, which is secure register allocation for trusted code generation, and these are very much important, right. So, any security allocation you have to compile your program. So, suppose you have a AES program, you need to run it on a processor, you have to compile with GCC or LLVM, any compiler, right. So, you must aware what is happening inside compiler, can I trust the compiler, right. So, I will talk about more on this secure register allocation now. As Professor Mishra was talking about, that any kind of security work, the first thing is the threat model. So, if you do not know your threat model, you cannot give a solution, right. So, what is threat model? You have to decide what are the things attacker have access to. Okay. So, we assume that attacker has access to the memory at the end of the execution and do not have direct access to the register values. So, why this kind of model is makes sense? Because the memory is more stable and you register value change very frequently, right, maybe in every clock it gets changed. So, attacker has less control to see what is there in the register, right. So, whereas some value is there in the memory for longer time. So, he has more opportunity to the attack to try to see what is there in the memory, right. So, what you assume that your memory can be accessed by the attacker at the end of the execution of the program, but during execution of the program the register's value is very unlikely to be accessed by the attacker. But if you assume that it is also possible, then you have you will see there are more security flaws, right. So, it depends on which threat model you have considered for your work. Okay. So, as I mentioned, what is register allocation? You have a say program like this, these are the operation is happening and these are the variable getting defined by this operation. So, this may be a plus, this may be a minus, this can be multiply and so on, right, and this is the data dependencies. And register allocation, what it does? It basically takes these variables and map to the registers. And as I mentioned earlier, your objective is to reduce the number of register usage. So, for example, you can see here that this V1 and V7 map to R1, right. So, something like this. So, you can utilize the same variable to store multiple values, which is possible. So, in general the data flow does not change because of the register allocation, because it just rename the variable with the register. Whatever the data flow is happening here, the same data flow is happening here. So, there is no change in the data flow, only where you store the values is getting changed. Okay. So, I will give you example, some interesting example of register allocation. So, suppose you have this program where you are reading the password in A and you are doing some computation. These are all just small function just to show you the impact of those kind of register allocation. So, as I mentioned that your objective is to map this variable A, B, C, there are 3 variables in your program, right, A, B, C to register. One solution is that you put A into R1, B into R2, C into R3. But how do I know whether I can share a register for 2 variables? You remember the lifetime, right. If you have you know where A is first defined, where is last used, that is the lifetime of the variable, and if there are 2 variables whose lifetime is non overlapping, that means they are live in different phase of time, they can occupy the same register. Just like say I am taking class here, maybe from 12 to 1 some other professor will come, so he can occupy the same classroom, right, the same concept, that if 2 things are non overlapping, they can put into the same place, right. So, here the lifetime of A is basically the entire thing, because you are using almost everywhere, right. The lifetime B is this and this. So, you can see here they are non overlapping, right. So, they are basically have overlapping, right. So, they are basically they are live at the same time. So, that means you need basically 3 registers, right, and usually that has been modeled as a dependency graph. So, if say this is A, so they are have overlapping. So, A to B there is an edge, A and C. So, this is A, B and C, right. So, A and C also have overlapping. So, A and C an edge, and B and C is also overlapping. So, B and C an edge, right. So, usually this is how we do this, and once you calculate, so this is what is called conflict graph, right. So, when they are conflicting to each other, and this is basically after that you do a graph coloring, right. So, if you basically put the same color to the some node such that they do not have edge between them, right. So, what is the graph coloring problem? You remember that I want to color the node of this graph with minimum number of color such that 2 nodes have a different color only if they do not have a edge between them, right. But here you can see that I have, if I put a color blue here, you have to put a different color here, because there is a edge, right. So, maybe it is a red, and since this is blue and this is red, this and both are connected here, I have to give some green here. So, I need basically 3 registers, right. So, in this example, if I do this, I have 3 dedicated register for this, right. So, R1, R2, R3, and after register allocation, all the A will be replaced by R1, all the B will be replaced by R2, and all the C will be replaced by R3. So, this is how I will rewrite and my program will look like. Understood what is register allocation? So, this is what the normal one. Now, if I ask the question, can I store this variable in 2 registers, is it possible? So, that is what register optimization does, right. Normally, you cannot do it, all agreed, right, because there is a dependency among all of them. I need 3 color, hence I need 3 registers. Now, I will show you in a moment that I can actually do something in this program, so that I can store all these 3 variable in 2 registers. Okay. So, what I will do now, see this I already talked about 3 registers. What I will do now is basically the splitting. Okay. So, what I did is basically that SSA what I talked about earlier, right. So, what it does, there are 2 definition of A, I make it A1, I make it A1, I make it A2, and this usage is here A2, right, and this is also A2. So, if I do this, this is called splitting. Now, their dependency will become like this. Okay. You can see here they are overlapping, this is overlapping, this is overlapping, but there is no overlapping between A2 and B or A1 with A2, A1 with C. So, now the modified dependency gram looks like this. You have dependency between A to B, right, A to B, A2 to C, A2 to C, and B and C. Okay. Now, I can use colors, say suppose this is my red, I can put red here also, there is no edge, right, and I can put yeah. So, I can put sorry, I will do this way. So, what I will do is I will put green here, okay, and green here, red here, right. So, this is what I will do. Now, I can put 2 register for this. Okay. So, this is what exactly compiler does internally, try to split the lifetime, so that it can reduce the register usage. Okay. So, now I can map this A1 and C into R1, B and A2 into R2. Okay. Make sense? And you can rewrite the program according to this mapping. Okay. So, the same program which normally need 3 register, I need now 2 registers. Okay. So, this is what splitting, and now I will talk about one more cases. Let us say I have a program like this, which in general the dependency is this. So, you need 3 registers, right. Now, can I do it with 2 register also? Now, you say that oh you have same variable, I will make it A1 and A2, and does it help? It is not, because there is a click of 3. So, you need R, G, B, and this can be R. So, I still need 3 register. Okay. So, the live range splitting is not helping here. Okay. So, what will so the splitting is not helping. So, can I do still mapping with 2 register? Okay. Understand the problem, right? So, sometimes splitting helps, the previous example. In this example, splitting is not helping. Okay. So, even if I do the splitting, I need 3 registers. So, now I will show you a way what compiler does to make it use it 2 register to do this, which is called spilling. Okay. This is called spilling. What is spilling? It is basically you spill some values to the memory when it is not being used, and you bring it back whenever they are being used, right. So, that I can use less register. Okay. So, if you take the same example, what as I already mentioned that you need 3 registers, but say available register is 2 hypothetically. What I am going to do is now is this. I read the password in R1 and I store back to memory M. So, although I read the password in R1, but it is now in memory, right. So, R1 is free. Then I read the value of, so B is basically my R2, read the value of C in R2, and then R1 equal to R2 plus R3 I am doing here, okay, which is basically I should have here R1 equal to B. So, basically I am using R1 to store B and R2 to C. So, now I am doing these 2 operation, but now I need A. So, what I will do, I will bring that value from memory to R2, from memory to R2, because after that I need only B, but not C. So, I can clear C from memory R2 and I bring the value of A from memory to R2, and then I will do this, right. So, this is basically with spilling I still able to do these things with 2 register, right, with 2 memory spill, right. So, I just spill the value to this A to memory and I bring it back by load store. Yes.
So, this one question, this is the optimization technique.
Yes.
So, I mean, sir, in this we are having a memory access which is much more overhead than the register access. So,
yeah. So, yeah, I mean your question is understood. So, in general this is a 3-line program, right, but if you think about your program has say 200 instructions and you have only 16 say register. In a processor usually you have 16 32 register, not more than that. So, practically you cannot keep every variable in the register. So, this is a very common in practical case, it does that, otherwise it is not able to execute things, right. So, what it does, I will show you the LLVM compiler, whatever benchmark we have taken, in all cases they are doing spilling, and it is just to because the number of register in your processor is fixed 16 32 and so on. So, that it has to do this, and this is the only way you can do it. Okay. So, this is basically we have analyzed this, since this this splitting, if you see in that sense we are not because everything is happening in register. So, and we assume that register is safe for us, right. So, we are not bothered about the normal allocation or splitting, they are good, but we say the spilling is not safe, because the very simple reason, you do not need rocket science here, because we are storing the sensitive value into memory, and although you store back into load back into the register, but the value you are not erasing there, right. The very simple idea is that we are not erasing the value from the memory. So, the value of password will remain in the memory location M for the time, I mean all the time, right, because you are not erasing, right. So, this is the kind of security leak comes because of spilling. Any question here? See, I am not giving any formal mathematics and all, I am just giving conceptually. You have a sensitive value, you put it to memory and you forget to erase it. So, it will remain there in the memory, your program is getting executed, but that memory location will be allocated to somebody else later, and he can write something there, and from that value change, which is basically the power analysis, you can identify what was the value earlier, right. This is how people can do it. So, this spilling is not secure, that is what is our conclusion, understood, because we are putting sensitive value into the memories. Make sense? So, solution is very simple. We basically took the LLVM compiler, which is kind of de facto compiler nowadays, everybody use LLVM, and is very very efficient compiler. Everybody use LLVM nowadays. So, we identify that it has 4 different register allocation scheme inside that tool. Okay. So, we took one of them. So, the greedy one, the bit is default, and the modification, this is the tool flow. I do not want to go into detail, but what exactly we have done, we identify the last reload, when is the last time you are loading from this memory, and you simply clear that value, right. You just clear the value, that is all. So, the solution is very simple. Once you identify the problem, solution is basically in security term, you just erase the sensitive value, right. That is what we are doing. So, but implement this, you have to understand how things being done in the tool and what is the kind of solution you are doing. Okay. So, so just to show you that these 4 register allocation schemes are there in the LLVM, and this is the total number of leaks, right, by our tool, right. You can understand that for every benchmark it is actually leaking. This is the number of leaks by your program, and then this is our secure one, because we are so this is basically the number of, you can think about spill, right. This is basically the leak equivalent to spill. So, this is the terminology I want to highlight here, that for every benchmark it actually does spilling, right, and every spilling we are assuming it is basically leaking, whether it is a sensitive value or not, that we can cross check, but we have more opportunities, right, and because we are clearing them, we are saying that we are basically erasing this leak. Okay. So, this is the overhead in terms of what, because we are actually adding some instruction. So, it is basically how many instruction is getting instructed in the number of k, what is the number of cycle you are the modified version of the code, because you see this many cases we have to add load 0, right. So, these are many instruction you are adding. So, it has some overhead in the number of instruction to be executed, number of clock cycle you need to do this, and so other parameter, but in general the overhead is very low, because you are just adding one instruction for each load store, right. So, it is basically less than 1% in by our tool. So, yeah, so this is what about the secure register allocation. So, probably I will take a break here and then I will talk about this quantifying information leakage after the break. Okay. Thank you. Any question? I hope I am able to establish that compiler is cannot be trusted, right. So, it actually does lot of sensitive things for us. So, we will have a 30 minutes break, 11:30 we will come back.